Okay, I'm going to give a presentation on backstepping controller for fast tracking of ROS-based differential drive mobile robots. And there are four main aspects to this topic. Firstly, I will introduce a mobile robot model, and secondly, backstepping controller is designed, and thirdly, I will show some simulations and a demo, and the last part is the results and analyze. And firstly, as shown in the picture 1, it is a real mobile robot. And picture 2 shows the coordinate system used to describe the mobile robot model. Here is two wheels, drive wheels, and this is the supporter wheel. And we use XC and YC and theta C to describe the pose of the robot in the inertial coordinate systems. Okay. Firstly, the dynamic model of the mobile robot used can be obtained based on the Lagrange formulation, and is given by equation 1. And here, U is the vector of the linear and angular velocities of the robot, and tau. Tau is the vector of input torques on the wheels. And BX, FUX, and G is showing here. It is the kinematic and dynamic parallelogram properties of the robot. As shown in the equation 1, we should know that the first expressions of equation 1 is a kinematic function and model, and the second expression of the equation 1 is a dynamic model. So the input is tau, and here kinematic model, the input is U. It is a cascade. There are a cascade between dynamics and the kinematic model. And most work have done before just control the kinematic model of the equation 1. So here we needed to design a backstepping controller. Firstly, we can do some user feedback linearization, like equation 2. Tau equals to this form, and linearize the second expression of 1 to obtain equation 3. Here, the second expression become a linear equation. So the next, we need to do some coordinate changes, because controller for equation 3 is designed under the assumption that the robot should be converged to the origin. However, it is interesting to stabilize the robot at any pose. So it's a simple coordinate change. Next, for the first expressions, we designed a non-smooth controller. By considering a coordinate change, which is similar to a change to polar coordinates. Equation 5 to H is the first expression of equation 1, and UE eta 1 and eta 2 is the input. Now the first expression of system model 3 can be rewritten as this form, which is the first to converge to the orange by the following input signal. It can be easily proved by a Lyapunov function. So using this, we can control the first expression of system model 3, and then next step is backstepping, and by applying the transforms 4 to 7 to 3, it is possible to write this form. And here, the inputter is become mu1 and mu2. Rearrange the equations by replace E1, E2, and mu1, mu2. Here we get the equation 20, get this form, and then by replacing eta 1 and eta 2 from 13 and 14, we get the equation 21. And then let the following candidate to Lyapunov function which by differentiating with respect to time and replacing the system equation from equation 21 gives we get the equation 23. Then by choosing mu1 and mu2 in the form without we can get the v.1. This proves that v1 is indeed a Lyapunov function for the system 21. Then eventually we get v1 mu1, and we get eta 1. So we get mu1. So this picture 5 shows the whole process of the controller design. So next step, another question is how to calculate the odometry for differential mobile robots. All flexible trajectories are composed of across of circumference. The straight line is just here. This is the arc, and this is the straight line. And in the road system, we choose the arc to make the calculation of the odometry to be more precise. It's something of a geometric relationship, so we don't show the detail. And next step, I will show some demos and simulations.
So is this gazebo or no?
Gazebo.
I mean, you are sharing desktop. I can see, Team Viewer.
Yeah.
What is this environment?
This is the gazebo.
Oh, gazebo. That's what I'm trying to ask. Good.
This is the ROS ID, and we just need to every node be right in the launch file, and just one launch file we can get a simulation. And this is the differential driver model, a mobile robot. And I just give a command. Just need to give a command. It will, okay. I will turn it on, and it will move. And in the other terminal, I can. You can see the data.
That's cool.
I just stopped and the data, the value don't change. So we give another command. It will go back, and you will see the data.
I see. So what controller was used in this demo?
Backstepping.
Is it already backstepping?
Yeah.
Your algorithm.
Huh?
You put in your algorithm, right?
No. Online code.
Sorry?
I find the code online, and I just put it together and make it work.
But if you want to change the controller, you know how to change.
I try to put a fractional calculus, but I do not find a good mathematical method.
But say, for example, let's do a fractional order PI or PD control.
Okay.
It's possible?
And actually, I found the PID controller for this one, but
okay.
The result is not as good as this one.
Yeah.
So,
good. So you don't have to do a real robot experiment on the floor.
Yeah.
So this is called a gazebo platform. It's amazing, very useful.
And let's see some results first. Here we choose the result of step in x0 direction. In the picture, it is possible to see the offset at the initial point of the trajectory, and the robot convergence to the trajectory. The arrow is small, and actually this is 1 meter, and here is a point 0 point. Most arrow, the max arrow is point 0.07. Maybe it's small. And this picture also shows that the reference pulse and the robot pulse over the time, and the pulse of the robot will converge to the reference values. And next is the result of a step in y direction. We know in x direction and in y direction is different, because the robot cannot move immediately to the y direction from x direction. So the arrow is a little bigger than x direction, x0 direction. But the final result also shows that the robot pulse over the time, and they will converge to the reference value. These two examples is point to point. And next I will show something about trajectory checking.
is under Linux. Everything.
And in this case, gazebo and always be launched at the same time because the gazebo is more suitable for simulation and always is a tool for realization. So every command is put in the launch file, so I just need to put it on, and we can see the trajectory of the mobile robot. And the right arrows shows the history pose of the mobile robot, and the blue arrows shows the next pose that the robot needed to follow. It will follow a trajectory of the shape of it. So it's at the orange pose here, and the orange point of the eight covers is here, so it follow here and slowly it follow the eight trajectory. Something like that. Eventually it will at the same way we need to we just show the results here. Eventually it will follow trajectory, and this is something loss node. This is the results at the beginning. The robot is at the pose of 0, 0, and the orange point here 8. And we can see that the result is good, and the arrow is small, very small. So, and this picture also shows that the robot can use the backstepping controller can converge to the trajectory. So finally, so this is the worker presented a controller for a mobile robot, which considers the dynamic model of robots. And finally, the performance of the controller was proved to be effective.
Good. So basically, the two demos are not they are compiled by you, but not written by you. Yeah. Is there other people?
The launch file is different because some command or the first without ROS, and the second put ROS into it, and put the command into it, and make the demo simple.
I see. So you did some modification. Did you? Did you do some change?
Yeah, because the voicing is different, so I have to make some change.
Okay. That's very good. So question? So Gazebo is very powerful, okay? You don't really have to real robot to do robot research, basically. All right, in the interest of time, let's thank the speaker. We'll move to the last one.